This paper exists actually from looking from one of the papers of Hamid Afshar. We were looking to some flat holography situation in 1+1, and then professor sent to us a paper, and we were like shocked because in the paper of Hamid Afshar there was unimodular gravity. And today I'm going to explain you how it arises and why it's useful, maybe.
Good. سلام. فرباد شما دانشجو دکترا هستین اونجا؟ ناتینگهام؟
بله، من یه دکترا تو ناتینگهام هستم، ولی فاندینگز من از رویال سوسایتی میاد.
رویال
سوسایتی ناتینگهام برامش میتونم ارج رو درس بخونم.
درست.
ولی از ایمپریال کالج من
درست.
سلام. آره. I will switch in English. It would be fantastic to do it in Persian, but I lack the technical words in Persian. Please stop me when you want. This talk is going to be very introductory. I will introduce as well JT gravity at some point, so it's going to be very basic, but with some important points, not trivial points. And yes, I'm a PhD student at the University of Nottingham, and this work was done with Alta Etkin from Southampton and Bruno Alexandre from Imperial College. And let's get into it. So let's go. So what I want to convey in this talk, it's 3 points, very simple 3 points. The first one, I need to make you understand in 4D instead of 2D. In 4D, the emergence of physical time in Henneaux Teitelboim unimodular gravity. what is unimodular gravity, what is Henneaux Teitelboim. I need to explain you and what it does actually, like to GR. Then we're going to discuss how this arises naturally in JT gravity, which is a very interesting point. And the third part is now that we have this technology of unimodular JT gravity, let's do a tabletop computation in the sitter to see what we can do, what we cannot do. I wanted to write here this a step towards the holographic interpretation of unimodular gravity. I'm working with that with Andreas Blumert from Institute of Advanced Studies, and hopefully we will find something interesting. But let's get to the first point, the emergence of physical time in HT gravity. I need to first say what is unimodular gravity. And unimodular gravity was basically introduced by Einstein. It's basically the first equation. I think you can see my pointer. So root of minus g equal 1. This basically is going to restrict our diffeomorphism to volume-preserving diffeomorphism. And it will give you the trace-free Einstein equations. In 4D, the action, as you can see, is that one. The most important things that I want you to understand from these slides is that the cosmological constant is now a function, from a Lagrange multiplier, and is enforcing the unimodular condition. So you vary lambda, big lambda, and you get the unimodular condition. And by conservation laws, this implies that lambda is as well a constant on shell. So it doesn't change from GR, but unimodular gravity changes because it's volume-preserving diffeomorphism, so it's restricting the diffeomorphism. We're not going to speak about this unimodular gravity. We're going to speak about HT gravity, the basically restoring the diffeomorphism version of this. So let's go see that one. So this is the restored diffeomorphism version of unimodular gravity, which was done in 1989 by Henneaux Teitelboim. So I'm going to refer it by HT or unimodular, but when I say HT unimodular, I mean the restored diffeomorphism, so the one that is exactly as GR. And how you do that? So basically, they change the unimodular condition, the square root of energy equal 1 to square root of energy equal to this partial mu t mu vector density type. And basically, this restores the diffeomorphism, and we call it unimodular condition. And this is exactly as GR on shell. Like classically, 100% is on GR. Tony Padilla from Imperial College, from Nottingham University, for instance, says as well the IR quantum. The quantum part, but classically is the same. As you can see it very quickly from equation number 2. So lambda right now is off-shell variable, but if you vary the T mu, you will get the on-shell constraint that is a constant lambda, and when you vary lambda, it will give you the unimodular condition here in 1. The big question: why people are interested in unimodular gravity? Why people are doing HT gravity? Why is this important? So the most important part, it gives you a time direction. So I'm going to explain you basically what I mean. So if we assume that our manifold topologically is like sigma cos R, and if you integrate both sides of the unimodular condition, you get a volume between two hypersurfaces and a difference of this T lambda, which we're going to call it as a unimodular time in equation 5. Why this T lambda is so important is canonically conjugate to lambda, to the vacuum cosmological constant. So it means that you can take it as a Poisson bracket that I wrote down here. It commutes with lambda. And basically, it means that as lambda, you can see it as an energy. T lambda is your coordinate time, a physical time that cares about lambda. This is very fundamental in the quantization process. So we have a problem of time in GR. And the problem with time is that when you try to quantize GR, canonically, you get the DeWitt equation. So you don't have an evolution, this one, basically, by the constraint on psi is equal to 0. That means basically that it's frozen in time, basically. The quantum states, you don't have unitarity. The Hilbert space is Hill-defined as well. So basically, what unimodular does actually, it's basically it change the Hamiltonian constraint. So basically, the Wheeler-DeWitt becomes a Schrödinger type of equation, and you get this partial T lambda in the Schrödinger equation, and basically it gives you a time direction evolution, a unitary evolution in T lambda. This is expected in some sense, and was noted by many people like Sorkin in the 80s and so on. The reason why we have this problem of time because in the Hamiltonian, in the constraint, you encode the space-time. So time that is something external in quantum mechanics is omnipresent, is ticking always, is missing in the quantization of GR because it's part of the space-time fabric. But what the intuition that I want to give you, unimodular time, unimodular gravity, is adding observable that cares about the evolution of lambda. So it gives you a type of a Schrödinger equation. It will give you, again, a unitarity and so on. So that's very interesting. And now, yes, please tell me any question. Go for it.
Hi, thank you. So I was wondering, is there any relation between this relational time that is introduced in this formalism and the relational time that was introduced by Page and Wouters in trying to resolve this
It is exactly the same. It's in our paper. It's the third part of the paper. So if you go to our paper is divided in 3 parts. The first part is we show how this formalism that I'm going to show you arises in JT gravity, and then at the Sitter computation. And the third part is this is actually Page Wouters. It fits in Page Wouters. So yeah, you're totally correct. I'm not going to speak here about Page Wouters, but yeah, I will refer you to go to the paper.
Thank you.
No problem. So yes, so now that we have understood a little bit of this HT technology, let's see how is natural in JT gravity and how it arises. Let me go. So first of all, I want to put here a paper of Hamid Afshar, and it's here. And while we browse in the literature, you see GT gravity or CJ gravity, whatever. You find this exactly a psi here, as you can see, with 1 minus the epsilon mu nu partial mu a nu, and indeed this is already unimodular. We're going to show you how it is unimodular, but this is exactly unimodular. And it's unrecognized by the authors, at least as far as I know, because they don't know about this unimodular business in 4D, I guess. And the question, there are many questions here. Why is there in the question 1? How it arises? Why they need the unimodular condition, if they need it? And we're going to address some of these questions. So first, I will give a very simple introduction to JT gravity. Please block me when you want. So JT gravity, you could write the Einstein-Hilbert directly and say this is GR, but it's not. It's topological. It's the Euler characteristic, as you can see. So Jackiw and Teitelboim basically propose a non-trivial action, which is this one with the dilaton phi, we call it, and a cosmological constant lambda. I want to emphasize that the cosmological constant, it is indeed, as you can see from the field equation, setting up the space-time, so R equal to lambda, maximally symmetric. However, the most important bit is this is not a vacuum cosmological constant. So in JT gravity, you get these 2 distinctions, a vacuum cosmological constant and the cosmological constant, as you see here, into lambda. And it will give you this field equation in equation 8 that are non-trivial instead of the Einstein-Hilbert of equation 6. So this is the big point. What Kanjemi and Jackiw discovered? So in flat JT gravity, they want in flat JT gravity admits a BF formulation. We're going to explain what is better, what is this BF formulation, but the general map is this one. So in equation 9, as you can see, you can rewrite JT gravity as a BF theory through ISO 11 flat JT, and by setting little lambda to 0. And Kanjemi and Jackiw, they were wondering what happens if we add a vacuum cosmological constant, which is big lambda, which we did in equation 10. It doesn't admit a BF formalism from ISO 11. It means that the BF is not gauge invariant in that case. And they come up with an ansatz to fix this problem. So they basically did a Maxwell extension of the ISO 11, which I call here ISO 11 plus U1 in the Lie algebra, and they get actually a BF theory. But at what cost?
Farbod. Equation 9 is partially correct, but you have to pay attention. I mean, only Poincaré is not enough for writing flat JT as a BF theory. So flat JT gravity cannot be written as a BF theory because it doesn't have the right trait. I mean, it doesn't have an invariant bilinear form. So the very basic idea to add the central extension is to exactly have the BF formulation, in fact.
In equation 11.
Yes. That was just a partial remark. So if you have flat JT without cosmological constant or without vacuum energy, let's say, you cannot write it as a BF theory because
really?
Because the trace. I mean, you don't have the right bilinear form.
I see. I thought that they did it in the CJ original paper. They write it as a BF, like in flat.
I'm not sure. No, you have to add this central term, which is.
But when you have the vacuum cosmological constant, so the big
yes, exactly. Yeah. In fact, the idea to add. I mean. One idea to have this vacuum energy term is to be able to write it as a BF theory. So the only BF theory models that we know in 2 dimensions are either JT gravity with cosmological constant and let's say that CGHS hat model. I mean, okay, you are going to that, so I'm not going to. I mean, you're just
we're getting to CGHS hat.
Yes.
Which is equation 12, basically.
Yes.
So no, but no, I thought that we can write a BF theory for flat, but okay, I will double check the situation.
Okay, we can discuss later.
Yeah, sure. Thank you for the remark.
Yeah,
and
sure.
But the most important thing is, as Hamid is saying, that with a vacuum cosmological constant, you need a Maxwell type of algebra, which is this central extended algebra, ISO 11 plus U1, for writing a correct BF theory. But the cost to do that is to add a gauge field under U1, which is exactly what happens in 12 if we rewrite it in the second order formulations. And basically, exactly this 1 minus epsilon mu nu partial mu a nu, this bit is actually the unimodular bit that we are adding, and basically it's emerging from the BF. The question that I asked, can we do the same for non-flat? The response actually is yes. So let's let's first have a digression. That was a map. Have a digression to how to write a BF theory for JT gravity. So first formulation of JT gravity. So basically, let's say with a non-trivial cosmological constant, we are under SL2R, both for de Sitter and de Sitter. And I can show you in equation 13, you can see basically the commutators that we can write. And from there, we build basically our curvature 2 form from our gauge connections. And we are here in a Einstein-Cartan formulation, basically. And you can rewrite basically the original action in a trace of a BF theory, where B basically is a 0 form and F is your 2 form. And by going on shell, by setting the torsion to 0, you get back the JT gravity in first order formulation. And the equation of motion are the same. Basically, I wrote in equation 15. So this is the standard BF theory formulation of JT gravity. And we can do that with an extended de Sitter algebra. So we are doing something that we're going a little bit beyond flat holography. So flat CJHS at. So we are doing a central extension. We are adding this I in the commutators under U1. And basically, you can rewrite your connection and curvature, as you can see, under this abelian connection curvature, which is F equal dA. You do the same procedure. So basically, from the trace, you get the torsion and the other terms. And basically, you get back by setting torsion equal to 0 to the Einstein-Hilbert, to JT gravity. With the cosmological, so here it's the important point. So you have a cosmological constant, little lambda, that is setting up your maximal asymmetric space, but you have as well a vacuum cosmological constant now that is big lambda, which is fundamental because as well in the unimodular 4D theory, the cosmological constant and the vacuum cosmological constant are more or less the same. In 2D, basically, this is the split. Because you can see lambda is under phi here, little lambda. But we need actually for unimodular as well lambda to be free. So for that reason, 18 basically gives you correctly the unimodular gravity. And now we're going to ask, is equation 18 unimodular gravity? That's our question that we're going to double check. So let's double check. And what we're going to see is that this theory, actually, you can rewrite it in a densitized form. So partial mu A nu, now A nu is a density. And basically, you get exactly unimodular gravity as we explained before. So you get the equation of motion of 20, which are basically by varying, if you vary A mu, you get partial mu lambda equals 0. So on shell, the vacuum cosmological constant is a constant. And then you get unimodular gravity by varying lambda. And we find that, of course, in 2D, everything gets easier. So when you integrate both sides of the unimodular condition, which is root of minus g equal partial mu t mu, you get basically that T lambda, your T lambda is just the holonomy of the gauge field. And the difference of course of dt lambda is the volume between two hypersurfaces. So indeed, you find for non-flat as well unimodular theory by a central extension. I must say there is two differences. So in CJHS at, the central extension is non-trivial. So basically the Maxwell algebra is non-trivial. Here the central extension is trivial because it's SL2R. And okay, now that we have basically our unimodular gravity, we can basically do a tabletop computation just to show you what exactly does. Because now it looks like I'm saying too many complicated words, but let's try to dissect it better. So we can do a tabletop computation in de Sitter and see what the new tools are going to give us. Let's see. So we will do closed universes in de Sitter, and we do a mini superspace approximation, which is in 2D very similar to ADM, so it can be uplifted to ADM. And we can, which is the metric that I wrote here, A squared. And we can see that H2 action in mini superspace becomes equation 23. So basically is the action for JT gravity, for the Sitter JT gravity, plus this dt t dot lambda. And we can very quickly calculate T lambda is minus A theta. And in de Sitter, we have these metrics in global de Sitter, basically. We're taking this example. Let's go. So I give you a representation of global de Sitter. This it's not a double trumpet. This is a Lorentzian de Sitter, so it's just a picture. It's not exactly what is going on, but you can see that you have a minimal length of your A to B when is T equals 0, A equals 1. And here from the unimodular condition, from the equation of motion, we can see very directly that T lambda is basically sinh of T. So it gives you a time direction. And when T lambda is 0, basically the universe has a minimal throat of A equals 1. If you have any question, please stop me and ask. And so now that we have this setup, we can calculate basically the Hamiltonian for our action, and the Hamiltonian basically becomes this Hamiltonian here. You can see in equation 28, or 27 is basically the definition of Hamiltonian, so we subtract the Lagrangian there, and you get basically equation 28, where the first part of equation 28 inside of the constraint, so if you forget NA in the front, you have basically CJT PT lambda. PT lambda basically is what unimodular is adding from the standard JT gravity. So everything that you see in green in all my slides is basically the extra term that the unimodular is adding always. And by varying the action of H2 with n, you will get that classically the constraint is equal to 0, which after quantization will give us the Wheeler-DeWitt equation. So this is the standard procedure. The amazing thing with unimodular gravity, with the technology that I explained to you guys, is that in the moment that you quantize, now you have this extra PT lambda momentum, which will give you this partial T lambda, which is going to change the Wheeler-DeWitt equation that I wrote in 31, expanded after second quantization, is going to give you basically exactly a Schrödinger equation in the constraint of JT, in the Hamiltonian, let's say, of JT. So you can see very explicitly right now that the Wheeler-DeWitt becomes a Schrödinger type of equation. And the wave function that this describes, of course, the hypersurface of the universe is the wave function of the universe by Hawking and et al. And so now that we have a Schrödinger equation, the question is basically, let's find psi. Let's quantize it. Let's see what we can find. So I need to give you a digression for like a pure JT wave function. So let's say that we are only CJT. So basically we have only the Wheeler-DeWitt without unimodularity. We have 34 basically, and we take the wave function solution as 36, which is very standard. It's this approximation, and you can have the 37 basically an expanding and contracting part of the universe, basically psi. From this, we're going to basically build the full wave function, as you can see. So now we have a Schrödinger equation and time evolution, as I said. So we can basically write the general psi. I wrote it in equation 41 very quickly. and where basically A lambda is the Gaussian amplitude. We have the freedom to have this Gaussian amplitude, and these little psi's are the classical solution of JT gravity. And we are basically, you can see, in this new psi, general psi from the Schrödinger equation, we have unitarity as well, which is obviously something that you don't have with the standard Wheeler-DeWitt equation. So here I basically show you explicitly the inner product, and yes, the inner product will give you unitarity. You will find 1, and this exactly defines physical states, and basically you have a physical Hilbert space as well, which is remarkable by adding this observer. So now we can plot psi squared, and when you plot psi squared, basically you can see how the evolution of the universe, what happens. I will explain you. I will dissect these graphs. So basically, the first graph here is for T lambda equals 0. So it's when our universe is at the minimal throat here. And so we are quantizing this metric. Now we're going a little bit off shell from this figure. And what we find for psi, we find that A is very oscillatory at T lambda equals 0. So when it's the minimal throat, A equal 1, because you can think about it that the universe doesn't know if it's contracting or expanding. And you can see that A can take any values between 0 to more or less 150. And it allows as well topology change, so A equals 0. So you could have, after the quantization of this model, you could have the universe shrinking to a point. So a Lorentz type of cobordism, so a circle going to 0 to a point. And in later times, you can see in T lambda equal 100, it becomes more WKB, becomes less and less oscillatory in later times. This is because basically the universe is expanding or contracting solely after, and the main interference happens near to the physics happens in the bulk. I needed to remark that we're not doing any of holography. We're doing actually bulk of de Sitter here, so we're not caring about the boundary situation. And apart the boundary of de Sitter is spatial. Basically here you can see that you allow topology change, and we have a fully quantization of this tabletop computation, basically, of de Sitter. Here I give you some quantum interference stuff, but more or less I think I gave you everything that I wanted to tell you. So let's do a little summary. So I showed you that HT gravity formation of JT gravity is possible for de Sitter, and flat it already exists. It's out. And we saw that describes a unitary quantum cosmology. We can describe it. We can describe a unitary quantum cosmology with it. And we have as well a little bit of a possibility of reaching a single point of A equals 0 when you quantize the theory, when you go off shell. I'm going to make you an off topic because I have time. So in unimodular gravity, as you can understand, is the unimodular condition is the most important bit, which is the root of energy equal partial of t. Partial of t, this time, which is canonically conjugate to the vacuum cosmological constant, appear in a very topological, it's a topological part of the action. My speculation is caring about topology change. We didn't do here topology change, like as like low Kosorkin topology change or Fade-Oker topology change. But I believe you can see T lambda as a Morse function, if you're familiar with Morse functions. Proving this is another set of, it's basically another project, but as you can see, already the unimodular condition, which is root of energy equal to this partial mu T mu, it's encoding when the matrix is degenerate, right? So, and let's say that we have here the Milne patch. Let's take, instead of global de Sitter, let's take a Milne patch, which is Sinch. Your T lambda is going to be Koch, and Koch has a critical point at t equals 0, where it pinches to a point, classically, without speaking about quantum. Because when you quantize, you go off shell a little bit, which is the point in this paper. But topology change, I think, is encoding unimodular gravity, and is not explored at all in 4D, 2D, or 3D. They don't explore it at all. So sorry for the remark. So what is the next part of this is what is the holographic perspective of unimodular time? Do we have it? Does it make sense? Can we as well derive HD gravity in the same manner from a BF from higher dimensions? This would be amazing. And what happens in your horizon black holes if it's useful? So, and there are other questions that I can speak for hours, but I will stop here. And please, if you have any question, please ask me.
Okay, thank you. Can I ask a question?
Yeah.
Usually, the gauge field that we add as this, I mean, in an off-shell way, we integrate in the gauge field A mu in our work. It also has a gauge symmetry, U1 gauge symmetry. You should have the same thing, right? In JT or in this extended JT case, right? What is the what is the role of this U1 gauge symmetry extra? Have you noticed this?
That's a good question. So you're telling me that basically you're asking me this extra.
Yes,
partial
exactly.
Extra U1 gauge symmetry. So in 1 + 1, it's U1 or R. You could say R as well. It is a case. It is a fortune that is U1. In 4D, it's not U1, for instance. It's more open. So, for instance, I have a paper that in 4D we put, but it's always topological. I mean, in the action. So, like partial mu A F, basically, it's topological in 2D F. It's not F wedge star F. So you could see it as a temperature, maybe. So basically, what basically my problem. So I would like to understand as well why CJHSAT needs this partial mu A mu. If you have any, because I read a lot of your papers or different papers, but I'm no mean an expert in this. And I know that these people that works in flat holography, they need the lambda to be not a constant, a variable. And the reason is because it's connected to the beta, to the 1 over temperature. Tell me if I'm wrong.
Sure, no, that's fine. I mean, exactly. So the motivation, the basic motivation to come up with this theory in flat case is to write the theory in the BF theory formulated way, and but it also has some consequences. I mean, the fact that you have one extra dynamical variable U1 gauge field here. From holographic point of view, leads to one extra zero mode in the for the, let's say, asymptotic symmetry group. And the reason is, I mean, we explained it briefly in our paper, but it's also not very hard to check. So if you have the equation for a mu, if you want to solve it, then, as you said, it's something like d mu, a mu being 1 or something like that. It depends on the background you use, of course. And then if you want to solve this and preserve the solution in the asymptotic way, you have to use both diffeomorphism and the gauge symmetry. They should both together preserve the condition or preserve the solution of this condition, and that means that the diffeomorphism and the gauge symmetry are somehow related to each other.
But I think from a unimodular perspective, maybe why I'm more or less here, because I'm from a unimodular background.
Yes.
Sure. We have the equation 20, right? Root of minus g partial mu to mu that you were telling me. For us, is another way of writing the determinant of G as a gauge field. So basically, we are not changing how do you say, the dynamics of the theory, classically at least, but we are rewriting the determinant as a gauge field.
Yeah.
Outside. So we are putting out the information of the determinant out, and I will see it as more as an observable, because in fact it changes your will and width.
And you have to somehow, I mean, well, from holographic point of view, you have to assume and you have to impose that the diffeomorphism does not, and gauge symmetry, any gauge symmetry, diffeomorphism and U1 gauge symmetry does not change this equation. And that would relate these to both U1 gauge symmetry and diffeomorphism together, and that's why, for instance, in the you come up with a kind of extension of Virasoro symmetry, which was the case for asymptotic symmetry of JT gravity. I think it would be an extension here with a U1 current.
Indeed, we were trying to do the boundary theory, like the IR, so trying to find a Schwarzian situation for this action 19 with Andreas Blumhardt. We were finding something strange, some spin connection coming out as well. It's more complex, but I can tell you that in flat is more. It's more, as I told before. If the Maxwell extension is a non-trivial extension.
Yes, of course.
And in SL2R instead, it is a trivial extension. You can do a transformation and take away the I basically in the algebra. The generator.
But somehow related. Can you say what would be the corresponding transformation in 19 that would give you back SL2R or let's say JT? I mean, is it obvious to you?
Yes.
Just from the
in the algebra, basically. So maybe in the algebra it's easier.
In the algebra it is clear, but how about in the action?
Probably in the first order formulation, it is easier as well. You can, I think we found it. You can rewrite. It's either R star. I forgot, but I I can send you as well a little LaTeX. We did it.
Sure.
You can reformulate it.
Because I think this term has has an important consequences. I mean, it is, even if at the algebraic level you get you can somehow mod out this central term, but I think still this new action, which is an extension of JT gravity, would give different boundary dynamics, kind of a.
Yeah. We were trying to do the bound until 2 months ago. We were trying, and we will continue probably. And it gives you an extra holonomy in time situation. But we need it's very early. Like for us, it's early. We need still to discuss. And another thing in JT, like everything is done in Euclidean. So So we need to as well ask ourselves what is unimodular gravity in a Euclidean context. Nobody did it, for instance. Now periodic or something like that. And no, it is interesting. But the main point here, I don't know. Maybe Hamid, you can tell me if you knew about it. But with CJHS hat, your Wille DeWitt will become a Schrödinger equation in terms of A.
Yeah, well, there we did not look at these aspects. I mean, it's, the motivation was more holographic, and we did not really look into the time evolution or something like
observables,
Wheeler DeWitt equation. But it is interesting. I mean, what you're saying, especially from JT point of view, maybe Behrad is more into this. But this topology changing, I mean, that could be. I mean, in the DS context of JT gravity, it has. I'm sure it has some consequences for JT gravity.
No, I'm looking a lot in topology change in the sense of the Hawking papers, right? The Cambridge of the 80s type of papers.
Yeah, but in CGHS hat, I mean, it's it could be interesting, but in the flat case, you don't have too many topologies anyway, because you're.
But I'm interested in Lorentz cobordism as well. If it's flat, you can have a canonical singularity, like a low consorting. So you can have a flat. So everywhere flat, but at the point of singularity is a conical singularity.
But then.
Because in 2D you can have two types of singularity. You have splitting of a universe or a creation of a universe. You cannot have much. And Loco and Sorkin, they do flat, everything flat with conical singularity. But yes, root of matrix goes to 0. You don't.
If you add conical singularity, then you have to probably add something to the action, no? Because then Ricci scalar is no more 0 identically. There would be some delta function. Maybe
there would be one delta function per conical singularity.
Yeah, but in the original form of CGHS hat, we don't have delta. I mean, we don't have any conical singularity in the action.
Yeah. No, I mean, equation 20 should encode those singularities. Equation 20, that observable we add the partial mu should encode in somewhat those singularities. And I'm interested because this is interesting because there is in 4D gravity people, they're trying to do the path integral of the unimodular gravity right now. And for instance, do it in 1+1. Okay, 1+1 is a different type of theory. We know it's topological and so on, yada yada. But it would be another step towards to that idea of path integral and topology change. And I'm interested in Lorentz cobordism, so in the Lorentzian case, for instance. This is as well very related to weak rotation of the matrix. So like you take G to be Lorentzian equal H to be Riemannian plus a vector field for Lorentz cobordism. But yeah, maybe I'm going off topic, but it's all of these are connected relationship. The beautiful thing that I always was looking in your papers is that you need lambda, the vacuum cosmological constant, the big lambda, to be varying for having a temperature that is running.
Yeah.
And this is the main point of unimodular gravity in 4D, for instance. Like they don't attach it to temperature. They don't have Euclidean versions, but it could be done in 4D and vice versa.
Mm-hmm. Yeah, it's interesting. I mean, I must say I had not noticed this. Simply people usually think that SL2R is a semi-simple algebra and does not admit any central extension. But okay, at the level of the action, you can still use this. It is interesting. Okay, but I would say it's more. From JT, people should be a new, let's say, topic in JT. For instance, the partition function, one-do partition function here would be different, I guess, from the JT. Or the
Andreas Blumart, I don't know if you know Andreas.
Yeah, well, I'm not sure, but.
Andreas Blumart is a postdoc at the Institute of Advanced Studies. He had a paper recently on observables, and he did some computation on basically our paper, this paper and he's saying that they're identical or something on these lines. But yes, I speak with him.
Is it out or no?
It is out. It's maybe 2-3 days ago paper.
Okay.
Last week. Yeah, it's from Andreas Blumart. I forgot the other people, but it is about observables. So, yeah.
Mm-hmm.
Yeah. I'm skipping a big part of my paper, which is page footers that Berad was mentioning before. But usually, when I give this talk, I get so many questions usually, and it's hard to finish it. But yeah, I finished it before. Probably because it's online. If it's in person, it's easier to see the persons and ask, shoot me a question.
Okay, thank you very much. Yeah,
Thank
any
you.
other? Yeah. I'm sorry, I just skipped. But maybe people have more questions. I'm sorry. Please go ahead.
Okay, if not, it was a pleasure to have you guys. Thank you for listening to me. ممنون.
Thank you, Farbod, for your interesting talk.
No problem.
Thank you. I wish to see you again.
یک سخنرانی انگلیسی از یک ایرانی با لهجه ایتالیایی.
من تو ایتالیا دنیا اومدم و تو
خیلی خوب.
درس خوندم.
خیلی خوب.
یه ذره خراب شده. ولی خوبه.
خیلی هم خوب. خیلی ممنون. من اگه نکته دیگه بود براتون می‌نویسم.
مرسی ممنون. My interest is in this right now.
Okay, sure.
Okay.
منم فقط خیلی کوتاه تشکر بکنم از همگی. خیلی ممنون. منم your talk was very interesting to me, but I think I have to go through your paper and also this paper by Andreas that you mentioned, and get back to you with some questions if you don't mind.
Yes, no, please do it. I'm going to see Andreas next week in Brussels, where there is holographic. And yeah, we're going to discuss a little bit of, I think he find the correct, there is a problem in inner products that we have in our paper, but I think he fixed it as well. But yes, please ask me, send me any emails. I don't know if you have my email, but or Gmail or my university email, please feel free to send anything.
Great, thank you. Thank you, everyone.
No problem. خدا نگهدار. خداحافظ.
خداحافظ.
خداحافظ.